proteins self-organize into pattern. I showed you all these pretty pictures. I showed you the chemical reaction scheme. I showed you the mathematical equation, but we're not done. I could switch on the computer, of course I could. I could plug in all the equations, could plug in all the rates as I can infer them, and I can represent or reproduce the phenomena. But for me, that's not understanding. So what we want to dig into is, how do those proteins actually self-organize into patterns? What are the most basic underlying principles for that pattern formation? All right, that's a goal. Then a question which is linked to that is, what is the role of the reaction circuit? And I alluded to that a few slides back, where I asked, should we even start doing a theory in the face of the complications that, as you have a chemical reaction network, in a few weeks or months or years down the road, this will be more complicated. So you have to ask yourself, what is the role of the reaction network? How important is it? And what features of the reaction network give rise to what kind of features of the pattern formation? There could be different things you think of, right? You could ask yourself, as I change the biochemical reaction circuit, do I change the pattern? But that's only one question. The other question you could ask is, how much variability do I have in the reaction rates to still have the same pattern? And that's addressing the question of how robust are those patterns to changes in concentration. And that's a very important question in biology, because it opens up the possibility of evolution, since, as you say, you have a robustness to changing a reaction rate. You could just even double the protein of that type and still have the same pattern, and then you have a pathway of evolving new reaction circuits and new ways of creating function in a biological system. So that's the second question we want to address. And the third one is, are there some general underlying principles? And that's asking way beyond biology. This is asking, can we somehow open up a new chapter in the theory of pattern formation in nonlinear dynamics and provide a framework that allows us to understand those systems in general, not just for biological systems, but also for technological systems and arbitrary non-equilibrium systems. And I believe, and I hope you will be convinced also at the end of the lectures, that there are some very general underlying principles which have a broad range of applications. So how am I doing with time? 20 minutes. Okay. Let me think for a second. All right, so this is now to introduce nonlinear dynamics to those who don't know it. Maybe for those who know it, there's something you can learn from it. And what I need at the end of the lecture when I teach about this, and this will be slides because I'm trying to, this is standard lecture stuff in books. So what I need from you is feedback concerning, was this on nonlinear dynamics, was this useful or just boring and I knew it all? Because I need to gauge the level of presentation for the next lectures towards what you know. You know, I have to teach to you, I know the stuff, so you have to learn it. So you have to tell me what you know and what you don't know. So nonlinear dynamics, some elementary concepts and ideas. And maybe to start out with, nonlinear dynamics is not solving equations analytically. You can't do this. This is just very rare that you're lucky to find an analytic solution, but you don't have to give up. If you don't have an analytic solution available, there's still a lot of interesting math you can do. Namely, you can look at the system geometrically. And this geometric viewpoint of a dynamic system is really, really useful. And it gives you answers in a shot. While looking at the equations, you have no idea what's going on. So let me show you. So here there's a differential equation, and I would give you that equation. Just for a moment, don't look at the rest, just look at that equation with an arbitrary function f of x. How would you tell me, by looking at the equation, what the solution is? Not so easy. If I write down an equation, this could be arbitrarily complicated, could be a long, long function, and you would have no idea by looking at the equation of what happens. If I plot the function, the solution is obvious. So that function here, f, is just this n-shaped function going down here, up here, down there. And now looking at this function, you immediately know what's going on, namely the function is positive here, it's negative there. So it means if I have a value of x being here, then the next time step, this value has to increase towards this point. And if I'm here, f is negative. So if I look at the time evolution of x, it has to become smaller. So in the end, in the long run, you will end up at this point here, which is called a fixed point. And similarly here, the flow, so the time evolution of x to the right and left is in opposite directions. So that point here will be a unstable point. And that just proves the point. So once you have the function and you plot it, you know the time evolution, at least qualitatively. And now I come back to this question of topological equivalence. Right? So if that function here looks like so, it's still topologically equivalent because it does have one unstable point in the middle and two stable points on the side. So whatever you do to this function, as long as you don't deform it to change that topological structure, you get the same kind, the same type of dynamics out of the system. And that's teaching you a lot already at the level of this very simple example. If you want to write this in terms of more traditional picture, you can actually in one component systems rewrite this right-hand side, the function f, as minus the gradient of a potential, and then these fixed points simply become minima and maxima of a potential. And then the same thing is true if you think in terms of this potential landscape. This is an unstable point, and as you move towards the right or left, you will fall towards the minimum. This minimum is stable because if you go up and to the left and right, you're driven back by some kind of forces. Now, this may change. This topological class here of behavior may change as you change parameters. So you can change here variables r, which characterize the shape of that function. So let me go here. So you can change this variable r here in such a way that you shift this function f down. And then you see you have done something very dramatic to the system, because now this is still a stable fixed point, but those two fixed points here, this unstable one and the stable one, they have merged here such that this one is here, doesn't know what to do. It's, so to say, semi-stable. It's neither stable nor unstable. And once you move down even further, those two fixed points will have vanished, and you're left with one stable fixed point to the left. And that's what's called a bifurcation, a qualitative change in the flow of your system. You change from one class of topological equivalence to another class of topological equivalence, namely just with one fixed point left. And you can visualize this as well in such a potential representation. So far, so clear. So is this trivial to everybody? Okay. Now here is this in more detail. So you can have a function f. This function f is characterized by some parameter. The parameter shifts down this function f. And as you can see, there is no fixed point here. The flow is just such that x always grows because f is always positive. Here there's a fixed point because here here there's a point which is semi-stable, and here there's a point where you have two fixed points, one stable and one unstable. So as you change those parameters, there is bifurcations, and these bifurcations can be visualized in this diagram. And what you do here is you plot the equilibrium value, the fixed point value, and I will use those names interchangeably, fixed point and equilibrium. I don't mean thermal, I mean really equilibrium in terms of a dynamic equation. So these equilibria or fixed points are such that there's none for r, a parameter less than 0. That would correspond to this situation. There's a special point r equals 0 where you're here, and once you're above r equals 0 at positive values, you have two fixed points denoted by this blue branch here. That's the stable fixed point, and the dashed branch here, that's the unstable fixed point. So what you see here is, if you look at those nonlinear systems just in terms of a graphical representation, you can quickly organize your mind of what the behavior is and how the asymptotic solutions of these systems look like here in terms of fixed points of the nonlinear system. Let's get on to an example. And this example looks trivial, but it's actually super exciting and interesting in a very different context. You'll see why. So this example here, let me look at this here. So you have a process with two particles, A and B, and these particles A and B, they can do two things. A can interact with B such that it turns B to an A. You can think of this as a contact process where B is a healthy individual, A is an infected individual, and the infected individual turns the healthy individual into an infected one. So by this contact between the two particles, you turn the B into an A with a rate that's lambda here. All right. The infected individual has a certain chance of actually recovering. So with a rate mu, it can go back to its healthy state, and that's it. That's the dynamics of the system. Now you can write down the equations for that, and that's a equation which has a mass conservation in it. Well, what's the mass conservation? Very simply, namely that if you add up individuals A and B, that number is constant, since all that happens here is you turn an A into a B or B back into an A. So the equation you get is one when you eliminate B just in terms of A, the temporal change of A is the infection process. So with a rate lambda, an A meets a B, so here you have lambda A times B, and as B is n minus A, you can replace this as n minus A, and then there is recovery with a rate mu, so you have dTA is infection minus recovery. That's the equation. So why is this equation exciting? If you look at this equation from that perspective, it's actually a very simple example of a nonlinear dynamic phenomenon. If you add diffusion to that, and if you add noise to that, that actually maps to a directed percolation process, which is very interesting to study. But that's just as a side remark. Let's stay with this contact process as it is. So now you look at that equation, and you can study the fixed points of that equation. And then as you study the right-hand side of this equation, they can do this as an exercise if you like. There is two possible fixed points that are easy to read off. So if you factorize the right-hand side, there's 1 0 of the right-hand side corresponding to A1 equal to 0. And as you factorize A out, there's another 0 of the right-hand side, another equilibrium, which is then A2 equals n minus mu over lambda. So there's two different fixed points, and they're possible candidates for equilibria. And now as a next step, you have to ask yourself, are those fixed points stable or are they unstable? Well, as you do the analysis of the simple equation, you'll figure that, this is not a battery, so you figure that this system here has a bifurcation or a change in qualitative behavior of the flow. And this change in behavior of flow, that depends on the particle number. So as you change n, you will change the behavior. And for me, this is the simplest example how I can show you that changing the overall number of individuals in a population has an effect on its dynamics. So here, what the outcome is, if n, the particle number in the system, is low, in that case, the A individuals actually die out. That's kind of an absorbing state. There's no more A particles. So actually the epidemic does not spread. Once you are at a threshold value of the population size, so at mu over lambda, things change. Now, instead of the absorbing state, so A1 equal to 0 being a stable fixed point, you have an interchange of stability. A1 becomes unstable, and A2, this is this fixed point here, given by a straight line, so n minus mu over lambda, becomes the stable fixed point. So that means the epidemic spreads, and you have sick individuals in the population in an increasing manner. All right. So that's a basic example which shows you that the population size here, the overall number, the mass of A plus B, has an effect on the bifurcation structure of such a nonlinear system. All right. Now going on to things which are slightly more complicated, and also in order to connect this with things you know from equilibrium thermodynamics, I told you that if you want to study those one-component systems, there's different ways of doing that. One way is just to write them as dtx equals a function f, or rewriting that in terms of a potential v. And if you write it in terms of potential v, then you can connect it to things you know from mean field theory of an Ising model. Here in this case, you have a potential landscape, and this potential landscape here is such that for various control parameters r, and you may think of this as the distance to the critical point, the potential has a shape which is a parabola opening up to the top, and then you say, well, the only fixed point here is the one in the middle, corresponding in the language of a ferromagnet to a paramagnetic state. Well, now you can change parameters such that this r here changes sign, and as it changes sign, this potential has this Mexican well potential with a stable fixed point, two stable fixed points at the sides at location plus and minus square root of r, and an unstable fixed point in the middle, and that corresponds to a ferromagnetic states with the magnetization being plus or minus square root of r, and the mean field exponent, if you like, is beta equal a half for that case. Right. There's a different situation. If you write this function in this way, where you change the plus here in the x to the fourth term to a minus, what you then have is that you invert the parabola, and now you have different behavior. So you start out with a situation where you have a parabola opening up to the top, but then the x to the fourth term dragging you down to the right and left. So that means there's a stable fixed point, but once you would go over those unstable fixed points, you would fall off the edge, and if there's no other term rescuing you, you would go to infinity. Now again, you can change parameters. You can change the r such that this changes sign, and as this changes sign, you have a parabola which is now completely opening up to the bottom. So you even lose the stability of this point here in the middle. So that's unstable now, and the system flows off to plus and minus infinity. So those are the two cases which I guess in thermodynamics you call this one here a second order phase transition, and this one here a first order phase transition. What is the generic case in thermodynamics? First or second order? Second? No. Second is very special. You need to fine tune. First order is typical. I mean, all the world has been discussing second order phase transitions, and they are useful to understand very interesting correlation phenomena in statistical physics, but they're not the generic case, they are a rare case. First order is more frequent. Yep. You could have that. So there could be a x to the 6th term, and what then does is the parabola goes down, and this drags you back up again. So in the end, even if you fall off the edge here and there, at some point there would be another another minimum, which would then rescue into a stable state. And that would correspond then to a first order transition. All right. So transforming that to a picture in terms of a bifurcation scenario, this is what it is. So here in one case, you have subcritical, and the other one you have supercritical. And that's a terminology not all of you may know. So this you would call a second order transition, right? And this you would call a first order transition if you think about thermodynamics. In nonlinear dynamics, this is called supercritical because above the critical point you have those two branches. And this is called subcritical because below the critical point you have those two branches. That's at least how I picture in my mind what super and sub means. And again, when you think about what is a generic transition in a nonlinear dynamic system, the answer is this is rarely the case because it needs fine-tuning. This is the typical case where you have a subcritical transition and not a supercritical transition. Now, what does it mean? Just let's remain here for a while. If I change a control parameter, like a temperature, and I go through that bifurcation point, what happens if I'm right next to the bifurcation point? Well, I have an order parameter, which is small. See, it starts out like a square root, so it's small. And that very fact is nice in terms of constructing a theory because it allows you to do perturbation theory around such a supercritical point. This perturbation theory may be super sophisticated and end up in some renormalization group calculation, but it's possible close to such a point because of the smallness of the order parameter in the vicinity of the critical point. In nonlinear dynamics, the same story. So if you want to do a mathematical analysis in terms of analytic formula, this is a very convenient situation because you have something small you can use for perturbation theory. The perturbation theory you do in nonlinear dynamics is called amplitude equations or singular perturbation theory, and that's a tool you can use in the vicinity of such a supercritical point. It's a useful tool and it helps a lot if that's the case. But as I said, this is not the case which is generic in a nonlinear system, as second order transitions are not generic in a thermodynamic system. And as you know from active matter, in active matter, the realization is that first order transitions are the generic case and second order transitions haven't been found yet, if I'm sure. There may be one or two cases, but they are, as we see, rare and the exception. So what do you do here? In the case of a thermodynamic system, the physics going on close to subcritical transitions is what? Phase separation kinetics. First order transitions, coarsening, these kind of things, Ostwald ripening, and so on and so forth. That's the interesting physics. So some kind of pattern formation, if you like, that goes on close to first order phase transitions. In the nonlinear system, it's similar. Here in that case, you're losing your standard tools because you can no longer do perturbation theory. As soon as you cross the critical point, you're flowing off to large values of the order parameter, and that doesn't allow you to do perturbation theory anymore. So you have to deal with a strong coupling case after you transitioned into the subcritical over the bifurcation point at r equal to 0. And as it turns out, and we will teach this during my class, there are very close similarities of phase separation kinetics to the ordering phenomena you have in nonlinear systems close to subcritical bifurcation points. All right. Now, one more thing before I close. Is about bistable systems and hysteresis, and I will need this as we continue. And you can easily capture that if you just transfer your knowledge from magnetic systems to nonlinear systems, and that's why I put it that way. So let's say you have a dynamics now that's described by this equation, and you can read this just as a standard model for a mean field Ising system, where you add on top of the 5 to the 4th potential a magnetic field. And this magnetic field changes the way the system behaves. So let's discuss the case r less than 0 for now, and that would be corresponding to a paramagnetic phase. And now you can ask yourself, what are the equilibria of this system here? Well, they're simply given by setting the right-hand side equal to 0. So by equating this term here, rx minus x to the 3rd, with h. And that's done here. So what I'm plotting here in this graph is this function rx minus x to the 3rd. So the first term here on the right-hand side, the blue line. And the external field here is just this horizontal straight line. And the way I put it is I took this function equal to minus h. And now it's clear what happens. So at r less than 0, the only possible intersection point between h and this function is a single point as you vary h. So we'll have a uniform relation between the order parameter x and the external field h. Things change as you move on to consider a case where the control parameter r is positive. That means you are in the ferromagnetic phase. And now as you're in the ferromagnetic phase, the line corresponding to the first two term on the right-hand side is no longer a monotonic function. It actually has this N-shaped form going down and up and down. And now as you do the same kind of game, you ask yourself, what are the possible fixed points of the system? Things are different, qualitatively different. And let me just go through with you. So let's say I have a magnetic field which in amplitude is large. Then you are intersecting this blue line with a red line at a single point here. So you have a single equilibrium point for that given field H. And now imagine lowering that field. And as you lower that field, there will be some critical value of the magnetic field, depending on the R value you look at, where you touch the curve here on the right-hand side right at the maximum. And then you have what I previously called a saddle node bifurcation. So as soon as you lower this curve H even more, you, in addition to having this fixed point here, you have a pair of fixed points on the right-hand side where one of them is stable and the other one is unstable. And as you go through, you will then enter at some point this minimum here in the N-shaped function, the blue curve here, and the game reverses. So this black fixed point and this open symbol here, they will meet here also in the saddle node bifurcation such that they vanish, and I have only one fixed point left here on the right-hand side. So what you see here is the paradigm of a system that shows monostability and bistability. So as you change the external magnetic field, there are regions where you're monostable on the left branch, and there's regimes where you're monostable on the right branch. And in between the critical value of the magnetic field, you are in a regime where you're bistable, two fixed points are stable, and one is unstable. And that's summarized now in this kind of bistability diagram, or a stability diagram, where what I plot here is the two control parameters of the system, one being just the distance from the critical temperature. So remind you, this less than 0 is in the paramagnetic phase, larger than 0 is in the ferromagnetic phase, and the other control parameter is the external magnetic field. And then you see a phase diagram such that in the white regime you're monostable, and there's a bistable regime where you have a cusp singularity right at h r equal to 0, where the two branches of the bistable regime actually merge. All right, so this is concerning the behavior of one component systems, the typical framework. You will have typically in these systems regimes where you're monostable and other regimes where you're bistable. And that summarizes it in terms of the structure you have. So for the particular case, so this exceptional case where you have a second order behavior, you have a bifurcation point which is called a pitchfork bifurcation. The fixed point at x equal to 0 becomes unstable, and you open up two branches of stable fixed points. And as soon as you are at h greater than 0, the way this happens is no longer in this symmetric fashion as for x equal to 0, but rather you have one fixed point remaining as kind of a spectator, and as this fixed point is spectating, there's a saddle node bifurcation happening at some critical value of r, where you have then a stable and an unstable fixed point. And if you want to read it even differently and ask yourself what would happen as I tune the external field up and down in such a situation, what you would get is that as you change the magnetic field from low values, you stay at the lower branch, you remain at the lower branch if there are no thermal excitations, you jump to the upper branch, you remain there as you go further in magnetic field, and as you turn back, there's hysteresis, you stay longer on that branch and you hop down at this point here. So that is typical for those systems. You have a hysteretic behavior, and now summing all this up into one single plot, you get this kind of figure where you have the control space of external parameters h and r here with the corresponding regimes of monostability and bistability, and the order parameter has the smooth behavior for the regime where you're monostable, and the regime where you can be bistable, you have this fold in the order parameter as a function of the two control parameters, characterizing this fall off or cusp singularity that you have as you change the control parameters. All right, so maybe with that, I stop here concerning the nonlinear dynamics, just to give you a rough idea of how you describe nonlinear systems in terms of geometry. And the punchline really is, and for those who don't know it, should look into this, the punchline is the way you analyze those nonlinear systems is not by solving equations. It's by looking at those pictures and trying to understand what those pictures imply in terms of the dynamics of the system. So it's a characterization of the system in terms of flows in phase space and changes of flow in that phase space as you change external parameters like field here and the temperature. So thanks for today.